Well, and this is it. A lot of you have already muted your audio. In case there are some feedback, check if your microphone is muted and mute your microphone. For the chat function, there is someone who is called Omicron Copilot, and so you can direct your questions to the Omicron Copilot in case you have any questions. Okay, so we will start the webinar with a simple question, and this question is, why do the presenters wear mustaches? And this is the only non-topic related question. The answer is very simple. It's Movember. And in Omicron, about 35 people participate in the Movember program. The Movember program is for men's cancer research to raise funds, and it's a worldwide thing, but in Austria it has just started. In America it's a lot more popular, and so we decided not to shave for this webinar, to keep our mustaches. So we apologize for our looks. So in case, focus on the slides and not on the video. And if you want to learn more about the Omicron Movember team, the link will be in the presentation. We will share the presentation after the seminar, so every attendee will get a link to download the presentation. This presentation is a repetition of last year's webinar. So we have made some small changes and amendments, but we found that there are so many people interested in loop stability measurements that we decided to repeat it as a first topic. After that, we will also do an impedance measurement webinar, and in addition, tomorrow there will be a measurement webinar on the measurement of non-invasive stability measurements of power supplies, so in case you do not have access to the feedback loop. So let's have a look at today's agenda. We will first touch base on the topic, what is stability? Then we will focus on choosing the right injection point. We will focus on choosing the right value of our injection resistor, choosing the right injection level, then perform a practical measurement, and then finally we will look at the results and interpret the results to find out if we have done a correct measurement and how to interpret the measurement results. So quite some program. The webinar itself will last roughly, I'd say, an hour. Let's see wherever the questions will lead us. So when we talk about stability, we first need to know our loop, our system, and there we are in a negative feedback system. This means we have the plant and we have the compensator, and our idea is that the output follows a certain input. So we have an input signal, and then we have our plant, and at the output we want to have the same like on the input, and to assure this we have a feedback loop, and in this feedback loop we get a feedback, a signal to the input. Now a negative feedback loop means that the feedback signal is subtracted from the input signal, and as a result, if I have a subtraction, then this means that I have a 180-degree phase shift of my signal, and so in the loop there is a 0-degree phase shift, but then I have this minus, and so as a result I have two signals which are 180-degree phase shifted, and I get a flat line, so the signals are canceling out each other. If I have a positive feedback, this means that there is a phase shift in the loop, and 180-degree phase shift in the loop. I have a so-called echo, I have an oscillation, so what will happen is that the signals will add up to each other, and then I have an instability and the circuit can start to oscillate. Why am I pointing out this minus all the time? Because in all the theory, people are taking into consideration that this minus will happen after they have looked at the entire transfer function, and therefore they are referencing against 180-degree phase shift. In our examples, we are referencing against 0 degree, and this we will show in a few minutes. So far so good. Now, next step is that we have a look about what we are analyzing. So how can we determine stability? To do so, we have a transfer function of the plant and a transfer function of the compensator. And both transfer functions together result in the so-called loop gain. So the loop gain is the product of all gains around the loop. In our case, we are looking at the plant and the compensator. And now, to know, by analyzing the loop gain, we can make sure that we have a sufficient stability margin. In the theory, there was Mr. Nyquist with his Nyquist criterion, and there are two ways to display this. On the one hand, we have the stability margins shown in the Nyquist diagram, and then we have them in the Bode diagram. The Bode diagram is the more common way to display this. So we see here the transfer function of our loop gain, and we have a pass-through frequency point where our gain starts to be lower than 0 dB. Lower than 0 dB means that the signal is attenuated. 0 dB itself is the point where the amplification is exactly 1. And the stability criteria says that as long as the amplification is bigger than 1, we are not allowed to have a phase shift that results in an oscillation. So for the Nyquist criteria, this would be minus 180 degree, because after that there would be the subtraction, which would add another 180 degree phase shift. So therefore, our stability margin here in the theory is measured from minus 180 degree to the actual phase. If we look into the Nyquist chart, we can see this as the phase shift between the -1 instability point and the real and the crossing of our curve through the Nyquist circle. On the Bode diagram in the phase, we can measure the so-called gain margin. The gain margin, it says if the signal is 180 degree phase shifted, then we have to have an attenuation which has to be significantly smaller than 1. We have here this blue point, and if you look at the Nyquist chart, this means if the signal is in phase with the instability point, then it has to be significantly smaller than 1, and here we can see the gain margin inside the Nyquist chart. So that's for the theory. Since we are measuring directly in the feedback loop, we will not be referencing against -1, so minus 180 degree, we will be measuring to 0 degree. Why is it that way? Usually in the theory, when people looked at this, they first looked for the plant and then for the compensator, and then they defined the loop gain as the open loop gain as this product, but they did not take care of the subtraction. This means they have to reference against minus 180 degree. In our case, we break the loop or we inject our signal directly into the compensator, then it travels via this subtractor back to the plant and then comes back at the output. And therefore, we have this minus in, and the minus is 180 degree phase shift. Therefore, from minus 180 degree, we come to 0 degree. Therefore, we have to reference all our measurements to 0 degree.
And I think this is quite easy to imagine. If a signal that travels through the loop comes back in the same phase, then this is positive feedback. So if we are looking in the back and we don't see a phase difference, then we don't have any phase margin anymore.
Yeah, signals that come back in phase with the injected signal add up to each other, and as a result, we have an oscillation. If the signal arrives phase shifted, it will be subtract itself from the injected signal, and therefore it's a negative feedback, and we will have a stable system. So the Bode 100 is an instrument that allows to measure the transfer function in system. This means that I can choose a point, for example, the input of a system, where I inject my AC signal, and then I can pick up the input signal at any position inside the chain of transfer devices, and then I pick up the output of this device, and then I can measure exactly between these 2 points. So I can measure the transfer function H2, for example, by picking up the output signal of this block with channel 2 and the input signal with channel 1. The advantage of the Bode 100 is that it is a vector network analyzer and a frequency response analyzer at the same time. So we can switch the input impedance for our inputs, and in this case we can switch it to 1 mega ohm, which allows the use of standard oscilloscope probes. And we use the external reference function so that we can use channel 1 as a reference.
Yeah, this is something that is a little bit specific to the Bode 100. So if you start the software, then by default it will start to measure S parameters. And if you want to measure a transfer function, then you have to first activate the so-called, we call it the external reference, such that the channel 1 connector is really connected internally.
We'll show this later on when we do a practical measurement. So how does the voltage injection method work? What we do is we break the loop while not breaking the loop. So that's the funny thing. What we do is we put a small injection resistor inside the feedback loop, and we inject the signal into the compensator, which then travels through the loop, through the plant, and comes back at the output. And then we compare the injected signal with the received signal. So by dividing the received signal by the injected signal, we get the transfer function of the loop. And this is while the loop is in operation.
Yeah.
So it's pretty cool stuff. The injection transformer itself, in the beginning we used just a standard transformer, but we found out very quickly that you need to use a wideband transformer that also has a very low winding capacitance to ensure that we are not influencing the circuit. There are certain conditions to select the correct injection point. In principle, we would be allowed to inject wherever we can do this in the feedback loop or in the entire loop, but it has turned out that certain requirements need to be met that this method delivers correct results. And what the first condition is that the impedance where I inject the signal is significantly higher than the output impedance where I receive my signal back. So a good point is always where, for example, if I have the output of my power supply, I have a low impedance because power supplies have a low output impedance, and then I go to the feedback loop, and after my injection point is the feedback divider, which is usually high impedance, and so this is a good point. Another good point would be, for example,
the output of an operational amplifier or op-amp input. I think that's the best points you can find.
And the second condition that needs to be met is that the transfer function to be measured needs to be significantly bigger than the ratio of the output impedance divided by the input impedance. So these are two rules of thumb. So if you think that these two rules are fulfilled, then you have chosen a correct injection point, and your measurement result will have the tendency to reflect the real behavior of the loop. Why do I say will have the tendency? Choosing the right injection point is only the first step in doing a correct measurement. Next thing is that you need to choose the right size of the injection resistor Ri. And the injection resistor needs to be significantly smaller than your feedback divider so that you do not change the operating point of your power supply. In addition, you choose the injection level with your feedback divider. Our injection transformer is a 1-to-1 transformer, and it's fed with a 50 ohm source. As a result, you will get a signal that is depending on the injection resistor. The smaller the injection resistor is, the smaller the injected voltage is. So, for example, on the curve that you can see here, if I have a 50 ohms resistor, I would only lose 0.1 dB in the injection transformer, and the attenuation at 10 ohms is already roughly 10 dB. So, and we will find out that typically for the measurement of a loop stability, it's important to use small levels. Small levels where our signals always remain in sinus shape. There is no clipping, there are no harmonics, so that in the end we can make a small signal measurement. Further on, a small injection resistor has also the advantage that the 3 dB lower bandwidth of the transformer comes down. So we can see here, for example, the 3 dB bandwidth for the 50 ohms. For 50 ohms is 17.4 hertz with our injection transformer, and for 10 ohms it's 5.9 hertz. What is important in addition? It's important that we do in-system measurements. This means your device on the test should operate as much as possible in an operating range, how it will be operated later on, how it's used later on. So for example, if your device on the test is powering a load that changes, you also need to measure it at different load conditions. So for example, if the load can go into standby and it uses less power, still your power supply is not allowed to oscillate. Also, an input filter has an influence on the stability, and therefore it's also recommended to measure the device on the test with the correct input filter connected. So in total to summarize, it's important to measure under all expected load conditions and with the input filter connected, and for sure also at different temperatures. If your device is, for example, to be mounted in a car that also runs in wintertime, then you need to make sure that your power supply also works at low temperatures and so on.
And Bernhard, something that I did nearly forget. Many people always ask, what kind of load can we use? Can we use our standard electronic load? And this is very important. We recommend not to use electronic loads, because electronic loads are electronic regulating systems itself, and the regulator of the load can influence the regulator of your device on the test. And then you will measure a combination of both systems, which is totally different maybe to your real working environment afterwards.
Absolutely. In addition, the load can add capacitance to your output capacitor, and then it directly influences the behavior of your loop. So you have to be careful. The best thing is to connect the original load. If this is not possible, then use a resistive load or try to rebuild the load as much as possible with the real components.
Okay.
Okay.
So until now there are no questions, but please feel free to send us questions via the chat function. We will address them immediately if we have time and if possible.
If we're able to answer.
Yeah, of course.
Okay, so here are some examples for choosing the right injection point. Here we have a device that has a voltage control loop and the current control loop. We can see the voltage control loop here by identifying the feedback divider that is connected directly to the output voltage. And in addition, there is a shunt resistor, and this shunt resistor is used to measure the current. And we have a differential input here, so the voltage drop between the high point and the low point of the shunt is equal to the current, and therefore this is our current feedback loop. So we cannot measure these loops at the same time, but we can measure them one after another. To do so, we need to break the voltage loop, for when we want to measure the voltage control loop, between the output voltage and the feedback divider. This is possible for power supplies with low output voltages. For power supplies with higher output voltages, you sometimes need to shift this point, for example, to the point where the feedback divider is the middle point of the feedback divider. But in this case, you need to make sure that the feedback input has a significantly higher input impedance than the feedback divider. Otherwise, you're making a wrong measurement. Yeah, so we will inject the signal here at point B, and it goes through R10 and C9 directly into the feedback loop, and then it comes back at the output via the shunt and the output inductor, and comes back to point A, where we pick it up again. To measure the current feedback loop, or the current control loop, we just put our injection resistor into the positive feedback, current feedback. We send in the signal into the controller. It comes out again to the inductor and comes back here, and here we can pick it up again. So this is how we can measure the current control loop, and it's the same method. The only thing is, since the system is controlled via differential signal, it's recommended to reference not against ground, but to reference against the negative feedback input or current feedback input. And to do so, we are using differential probes. Now, here again is a converter with voltage feedback. Again, what's the trick? We check where's the feedback input of this device. We go back, we locate the feedback divider, we find the output voltage, and then we know exactly where to put our injection resistor. The important thing is that we make sure that there is no bypasses to our injection resistor. So we have to make sure that all the signals that arrive at point A also are just going through the injection resistor to point B. There should be no shortcut that is shortcutting our injection resistor, because then we are only measuring a part of the loop and we don't see the real loop characteristics. Okay, so the next one is, again, this is now a pure a device with a current feedback here again. So we have a shunt resistor. It's again easy. We just find the shunt that is used to measure the current, break the positive feedback, current feedback, put our injection resistor in, and reference against the negative feedback. So it's very easy to do. All different topologies, but still same methods to find the injection point. Well, and this leads us already to our first example. Here we are, and I hand over to Florian for this measurement.
Thank you, Bernhard, for all the slides, for doing all the slides. I get the easy part to do. And I would like to show you how we will analyze this buck converter. It's a 4 to 60 volt input voltage buck step down that steps to 3.3 volts output voltage at a maximum output current of 1 amp. The switching frequency of this device is 200 kilohertz. So let's have a look at the circuit diagram to find the injection point. And as Bernhard has already explained before, this is quite an easy job. So we just locate the output voltage, then we check where is the feedback divider, and then we can find our feedback loop and analyze the injection point. Looking backwards to the loop, we see output voltage of a power supply of a voltage source is very low impedance, and the impedance towards the feedback is very high. We have 165 Ks here in series, so it's a very high impedance. So this is a very nice point, and we will break the loop, place a 10 ohm resistor there, so we actually don't really break it, otherwise the system wouldn't work anymore and we would be in a totally different point of operation. But we place this 10 ohm resistor, which does not impact our system very much, since we have 160K, 24K here, so these 10 ohms, they don't really change the system at all. In parallel to the 10 ohms, we place our injection transformer to apply the disturbance voltage of the Bode 100, so the output voltage of the Bode 100, in parallel to this resistor. Okay, we'll now directly go into the measurement, and we'll try to find the camera such that you can see the system itself. And Bernhard will now switch on the system, hoping that no smoke will come out.
We already had some smoke today.
Okay, so today we unfortunately broke our second example, so this will be the first example, and the second one we can do a different one, but we cannot do the one we planned to do actually.
Okay.
So it's running. We have now 0.1 amp, as you can see here on the amp meter. You can see 0.1 amp of load current, and we'll now go to, let's say, half an amp, which is half the current our supply can withstand. So half an amp, and I will now start the Bode Analyzer Suite. And a very nice thing with the Bode 100 and the Bode Analyzer Suite is that we can load files. So I will now load the file we have already done before. That's this one, I think. Yeah, this file. And all the settings we have done in the software and all the measurements we have done before are now again loaded. So we do not need to set up everything again, but we will go through the settings such that you know what to take care of. I will select the data to display, so no memories, and disable the memories. I say display only the data you are probably measuring or you have measured already. And a very important thing you should never forget is to switch on the external reference. This means you click on this switch and it should point towards the external reference such that the channel 1 is really connected to the receiver 1 and that the Bode 100 measures the gain from the channel 1 to the channel 2 or the transfer function.
And in addition, make sure that the 50 ohm resistors are switched off. So this will ensure that you can use standard oscilloscope probes, either 1-to-1 or 10-to-1 for your measurement.
Bernard, let's check if the probes are compensated correctly.
Okay,
Can we do that now, I think?
For sure. I will just now connect both probes to the same point, and if everything's fine, we should expect, we should get a flat line for both the phase and the impedance.
The gain.
No, sorry, for the phase and the gain, yes.
Now start the sweep.
Yeah, it's looking good.
So we are now starting a sweep, measuring from 10 Hertz to 1 megahertz. And we can see that up to 100K, 200K, 300K, everything is fine. Above 300K, we have some noise. Bernhard, what do you think about this noise?
Yeah, well, in fact, the switching frequency of the circuit is around 200 kilohertz. So above this, these are just distortions. And since we require a certain time to perform the measurement, this is a kind of noise that comes in. So there's nothing you can do against it, but you also can ignore it because it's above the switching frequency.
And we can't even calibrate that out?
No, because calibrating noise won't work, because by calibrating noise, you add noise. Well, and in addition, if the switching frequency would be higher, let's say if the switching frequency is about 1 megahertz, then we will not see any distortions in that area. Yeah. So for our measurement, it's totally fine. We don't have to do anything. The probes are doing fine.
Yeah. And this is something I can recommend. Manually adjust the probes until you get the 0 dB and 0 degree line, because then you don't need to take care about calibration anymore, and you can swap the probes probably, or we mark them with channel 1 and channel 2, and then we compensate them such that we get a flat line. And this is very convenient. We don't need to do the software calibration.
Further on, also this test is very important to find out if there is, for example, a problem with injecting signals into the braids, into the cables of the probes. I once had a case where we measured a LED driver with very high currents, and it was, as usual in the lab, it was kind of messy environment with a lot of cables, and we had the problem that one high current cable was in parallel of one of the probe's cables, and then depending on how we moved the probe, the phase changed. And so we were not able to measure the phase margin. And so it's always good if you make this test and then you move around your probes, then if you still have a flat line, you know that everything's working.
Okay. Perfect. So we move back the probe to its original location, and then we should get a result for the gain and the phase. Oh, and it seems that
yeah, I swapped this. I swapped the probes. Sorry.
Actually, it was me. I prepared it wrong.
It doesn't matter. Last presentation of the day. So we're done in a second. So I just swapped the probes.
Okay, great. And we already get a gain and a phase curve. So Bernhard, what do you think about this curve? What do you think about the measurement result itself? Does it look correct to you, or do you think that this is wrong?
I think this measurement result looks quite good because we have done the measurement before, but you can easily find out that it's not that easy. Maybe if you switch the level to 0 dB,
Okay, I will increase the level now.
And now you will get a nice curve again. You will see, that's nice. Oh, my curve is more beautiful, more level rules. But as you can see, we have now, especially in the face, you can see this very well. There are some steps in the face, in this area. And this is a problem that is caused because of clipping. So in this area, we have step sizes, steps in the face. And also, if you look here, the point where the curve crosses the 0 dB line has moved. And so the first thing is, it's always important to measure with the correct injection level. So what I do is, when I start to analyze a circuit, I start to reduce the injection level, and I reduce until the pass-through point is no longer changing. So let's start. We are at 0 dBm, put -10, and we have a look. Okay, it has changed.
I enter 0 dB again to move the cursor to the crossover point. It's now 18.5 kilohertz. And I reduce the level further.
Yeah, now we go to -20, let's say. The noise is getting more, especially at the low frequencies. But now we see that the point has only slightly moved. And if a rule of thumb is, you reduce your level in 10 dB steps, and as soon as you are able to add 3 dB again, so for example, go to -17, and it's not changing, then you're making a correct measurement.
So let's wait until the sweep crosses the crossover frequency,
okay.
And it is actually not change anymore.
Okay, so please go back to -20. Now we are able to measure the phase margin. Our phase margin is here 72 to 73 degrees, and we are also able to measure the gain margin by referencing to the point where the phase becomes 0. And here we can measure a gain margin of about -12 dB. So Florian, gain margin -12 dB, phase margin 73 degree. Is this a circuit you would trust? Is this fine for you?
In my opinion, yes. And the rules of thumb say more than 45 degree of phase margin and more than 10 dB of gain margin. Well, it depends a little bit on whom you ask. Some people are happy with 20 degree. Some people would like to have more than 60 degree. But in general, you can say with 45 degree, you have only one period, one overshoot. So you don't have multiple periods of ringing. If you have less than 45, you will get more and more overshoot. And if you have more than 45, you will get even less overshoot. With more than 70, you generally don't have overshoot anymore. Then you're getting a very damped system and a very good response. So if you prefer to have no overshoot, then you should have more than 70 dB of phase margin. So this system here looks really nice.
But I do not like how the curve looks at low frequencies, because at low frequency we have lots of noise, and people might get confused about it. Is there anything we can do about it?
Yes, and this is, yeah, we can change the level again, so we could increase the level again, but then we will get a wrong measurement at high frequency. So what we can do here is we can change the level with frequency, and we call this feature the shaped level. So I click on this arrow and I click on shaped level, and then I click on this button to open our shaped level window. And in this window I can change the level, so the level is displayed on the y-axis of this curve with respect to frequency. So I can say at 10 Hertz I want to start with 10 dBm, and at 1 kilohertz I will start to reduce the level down to -20, and then I keep the -20 for higher frequencies. And if I click OK now, and I can stop and start the measurement, otherwise I have to wait until it finishes the sweep and starts again. So I will stop and start again, and you see that the noise is already gone. And then we can check if the crossover point is the same. Yes. And so now we have a measurement that is without noise and a correct result. But Bernhard, something many people are confused with: what happens with the phase at this 10, 20, at 30 Hertz? What is happening here? Why is the phase jumping that much?
Well, in fact, the phase is not actually jumping. What's happening is that the phase shift a good loop can start at minus 100 or plus 180 degree. And the problem is, when you display a phase, usually display it only between minus 180 degree and plus 180 degree. And as a result, plus 181 degree is minus 179 degree. And therefore, we can have effects like the one we see here, where it jumps several times between plus minus 180 degree. But in the end of the day, this curve is stable. So we have here, we can also imagine that this curve starts here at 181 degree and then continues, drops below 180 and so on. So this is an absolutely correct measurement. And since our points have not moved and we activated the shaped level function, everything's fine.
Okay, perfect. So now we can probably change the output current.
Absolutely,
the load current. Because this is something we mentioned before. You have to measure your system under all load conditions, that are bad for your system. So we now store this curve into the memory to be able to compare it to the result we will see afterwards, to check if something changes.
Florian, do me one favor, please switch back to standard level, because we know that depending on the output current for this topology, we need to possibly adjust the level, and adjusting the level is always recommended with a level that is constant over the entire frequency range we are investigating.
Okay, I will switch back to standard level, and I will now show you how Bernhard reduces the output current such that the system duty cycle changes. And the duty cycle is also part of the transfer function of the buck converter, and this means also the Bode plot will change.
And as you can see already, we have a level problem. So the level is too high for this measurement. We have changed the output current. We reduced the output current. Okay.
Now it's gone.
The effect is gone. Okay.
It was the high level from before. I will now change the level to 0 dB such that you can see it again.
Yeah. Okay. This was still from the shaped level. Yeah. So this is if the signal level is too high, you have effects like these steps and so on. And now, what we will do is we reduce to minus 20, and we check if the minus 20 we used before is the same, is enough for this measurement, or if we have to go lower.
Okay, so I'm searching the crossover point again by entering 0 dB here at the cursor 1 and pressing enter, and we see that the crossover has moved towards 88 kilohertz, so the system got slower, and the phase margin is less now. It's 57 degrees, so it means less phase margin and a slower system.
And now please change to minus 25 dBm just to check if there is an influence on the pass-through point. And yes, there was a change, a slight change. So you see it even went down further, and we are now at 54 degree. So here we are coming into a range where the output of the Bode 100 is at the minimum. So if we go to minus 27 dBm, for example.
Let's see if something else changes, if it reduces further. But I don't expect so.
No, now it is stable. So this is, we can now just measure this curve. But what would happen if we have to reduce the signal level further? We had some systems where we had to measure with a signal level of minus 47 dBm. What can we do in this case?
Well, then you could add an attenuator, so a real attenuator, a physical attenuator between the output of the Bode 100 and the BWIT, for example, the injection transformer, to reduce the signal level further, if you need even less signal level. So if you now would like to have a cleaner curve at the lower frequency end, then we could again use the shaped level feature to increase the level at lower frequencies, and we won't go that high anymore because we have seen that the system is now even more sensitive to noise.
So when you perform measurements, you have seen it's important that you look at the load current and that you look at the temperature. Another point to look at is the supply voltage. If you have a certain supply voltage range, you also have to do some stuff, and so you might end up with a lot of different measurements. You have to measure at the minimum load and then the maximum load with standard supply voltage, then you do the same with the minimum supply voltage, and you do the same with the maximum supply voltage. So there's a lot of things to take into consideration before you can really say that the stuff is stable.
Bernhard, I will now change the supply voltage a little bit.
Okay.
So I change it to, let's say, the double, so 15 volts.
Okay.
The load current is still the same. And we can see that, again, the system behavior has changed. So we have now a third curve with different system behavior. The crossover frequency has changed a little bit, and therefore also the phase margin. But this time it got better again. So we now have nearly 70 degree of phase margin with that input voltage. So the higher input voltage did improve our phase margin in this case.
Okay. So this is how you do the measurement. So just keep in mind, if your input signal is too high, you will have some effects like steps and so on. Always try to reduce the signal level until the pass-through points are no longer changing. It is also sometimes important that for measuring the gain margin, you might require a different level than measuring the phase margin. So, and for this, you then have to use the shaped level function. And in the next example that we can't show live, but we have a stored measurement, we can show this as well.
So the next example we planned to show to you is an LED driver. And it's a boost LED driver that boosts a 12-volt battery voltage to a constant current through the LEDs. And since there are many power LEDs connected in series, we need up to 30 volts to drive the current through the LEDs. And the circuit looks like that. We have all the LEDs here on the right hand side of the left picture. And we have a feedback resistor, a current sense resistor, that creates a voltage that is proportional to the current that runs through the LEDs. So we have a current, actually a current source that is controlled by a voltage loop. So what we need in this case is we need to use differential probes. Since the compensator receives a differential signal and the system reacts with a differential signal that is proportional or that is reflecting the current of the system, we also need differential probes to measure these signals. So we add a differential probe at the input of the feedback high and feedback low, and we add a differential probe at the output of the system, which will measure the current directly that's flowing through our current sense resistor and also the LEDs. And with that setup, we can also analyze the dynamic behavior of this LED driver. So we have, as Bernhard said, we have prepared this measurement, but it doesn't work. So we will show you the.
Well, the measurement works. We just broke the board.
Okay, the measurement works, but the board doesn't work anymore during our lunch break. It somehow.
Lunch break? Break the board? Okay, sorry.
It's this one. So the result looked like that. Bernhard, what do you want to show? Do you want to
yeah.
something?
When I performed this measurement yesterday, I found out that the pass-through point for the phase margin changes and that the pass-through point of the amplitude, the gain margin changes a lot on the level.
Yeah.
And I found out that for a good result, I would require different levels for the for the phase margin and for the gain margin measurements. And to reflect this, I programmed the shaped level. And so here you can see, to remove the noise, I went to the maximum output level up to a frequency of roughly 200 kilohertz. Then I dropped the level to minus 15 dBm, which was the perfect level for the phase margin. And then after that, I had to increase the level to about 5 dBm to measure the correct amplitude, the correct gain margin. So this is something to be considered. How to do this? First, you just have a look at the phase margin you adjust the level until you have the perfect phase margin. You remember this level. Then you go to the other point for the amplitude margin. The gain margin, again, you adjust the level. And if the point is no longer moving, you know the perfect point for this signal, because you also should not have any noise in that area. And then I found out, okay, it's 5 dBm and minus 15 dBm. And then I programmed these two levels first. And after that, I said, okay, now I want to get rid of the noise at the low frequencies, and I increased just the low frequencies, and that's it. And that's how I got a nice curve.
Okay, I think we are already getting closer to the end. Maybe I can continue with the presentation. And we have prepared another slide for you. And this slide asks the question, what can you do if you can't break the feedback loop? And by breaking, we mean inserting an injection resistor. So what if you don't have access to the feedback loop? And there is a possibility that we call the non-invasive stability measurement, where we derive stability information from the output impedance of the power supply. And the output impedance we measure with a picotest current injector. We have a special webinar on that. That is tomorrow. So I think you have received all the login data. So in case you are interested in that measurement, we would be happy to welcome you tomorrow again.
Yeah. So it's same time, same station. So and this time we hope that we will have no technical issues, so that we can start in time. Further on, in about half an hour, there will be our next webinar on impedance measurements. Power supply engineer also needs to be aware about impedance parasitics and the behavior of impedances in relation to certain voltages in bias and so on. And as a result, we have decided to do an own webinar on this topic. This will start in about 34 minutes from now. Further on, we offer a lot of additional power supply measurements, like the non-invasive stability we will touch base on tomorrow, the output impedance, the PSRR, which is the power supply rejection ratio, where you can see what happens, how much of a ripple that is injected at the supply voltage of a power supply remains at the output of a power supply, or vice versa. If you modulate the output, well, how does it influence the input of the power supply, things like that, input impedance. So there are a lot of topics, and you can find for most of these topics application notes on our webpage. And in addition, you can send us an email to info@omicron-lab.com. That's a mailbox that Florian and I are monitoring constantly. So in case there are some questions, please do not hesitate to contact us.
And we have some minutes left. We will still be here for the next 5 minutes. So in case you have a question, please post it through the chat now, or if you prefer to send it via email, please send it to info@omicron-lab.com or at support@omicron-lab.com, and we will then answer you the question during the next days.
Yeah, so there is one guy called Omicron Copilot. That's the one that goes to the laptop I'm sitting in front. So in case you have a question, feel free to post it. Alternatively, as Florian said, send us an email and enjoy the rest of the day. For us in Austria, it's already an evening, but we have one webinar to come, so before we can have our beer.
And hopefully we see you again in the next one, in the impedance webinar, where we show all the impedance measurements that are possible with the Bode 100.
Oh, there's a question just came in. The question is, were you using an electronic load to adjust for the first example? The answer is no, we just used a purely resistive load. Florian will show these loads to you. So these are just standard resistors with a slider. How are they called in English, Florian?
I have no idea.
Slider loads. No. It's a pure resistive load.
Wire wound sliding resistors.
Yeah.
I have no idea, actually. I'm very sorry. And we have another question. Can you show the shaped curve used in example 1? Yes, you can do that. I just opened the file again. So that's this one. And click on the shaped level here. And this is the shaped level curve. So I'm not sure if this was the question. If yes,
So we first found out that minus 20 dB is the perfect level where there is no longer an influence on the phase margin, on the point where the amplitude gets below 0 dB. The gain goes below 0 dB. And then we said, okay, but now we have this noise, and therefore we just increased everything which is below this pass-through point. Usually you have to have a small distance, so our pass-through point is somewhere in the area of 20 kilohertz, and the noise stops, as you can see here, around, it's 100, 200, 300, 400, 500 hertz, so it's definitely enough if we just increase the signal up to 1 kilohertz and then slightly reduce it until to 4 kilohertz. So we have enough security that we have the right injection level at the point we're interested in. Okay, there's another question coming in. Any advice for using the gain phase measurement for adjusting compensation components?
Well, I think this would be another webinar. If you talk about the compensator, then there are many different topologies and many different compensators, and based on what you have, of course, you need to adjust everything correctly. So we can't give any rules of thumb there, but there are seminars we can recommend. For example, a seminar of Dr. Ali Shirsavar, Birich Digital. He is doing seminars on power supply design, digital and analog, and he is really showing how you start with the plant, how you set up the compensators, where you place the poles and the zeros of the compensator to achieve a system that is stable. And
but anyway, if you have the possibility to play around with a compensator, for example, in a digital system where you just reprogram your controller, or if you have access to add or remove capacitors, then you can do this and perform a measurement before and after, and you see directly the influence of your change on the loop behavior. Tomorrow we have a seminar at the time that we will have for the impedance seminar today. And in this seminar, Dr. Ali Shirsavar will introduce his WDS software, which is targeting the design of a power supply by using the Bode 100 and this software. So I think he will be also the right person for further exploring this question. Okay. Isn't there a phase rep function in the Bode 100 software to get rid of the phase discontinuities? Absolutely correct, but for our example, it's a little bit tricky to use it. Florian, can you please activate the shaped level, the measurement again? I think we just need to start the measurement.
Yeah, let's see.
And we need to go back to 500 milliamps. So, because, yes, we can use this phase rep function. The only problem is we need to put the reference point right at the beginning. So if you activate it, you see that immediately your phase jumps and it starts at minus 180 degrees, and now your phase is shifted. And now you need to find out what is the point where the phase is crossing the 0 degree line, or where to reference to assess the phase margin. And therefore, in this case, we do not recommend to use this function. We can use it for all discontinuities which happen after this point, after the point where the phase is getting from minus to plus. So, for example, if we set the start of the unwrapped phase to, let's say, 100 kilohertz, then it helps us at the end of the spectrum. So here you see a continuous phase. You see how the phase happens, but we cannot get rid of the first jump because this will shift our entire curve.
Well, we can if we sweep backwards.
Ah, yeah, you're right. We can sweep backwards. That's a cool stuff.
Let's try.
Yeah, but you need to put the start to sweeping backwards. You're now getting really this is a live webinar.
Yeah, well, let's see where afterwards.
And then you need to define the end. You need to use the end first. Activate the end and the begin. You just created an additional jump.
Okay, this is nothing the software was designed for, so I'm not sure if it will work. I think we have to set the begin.
Oh, maybe the start, yeah.
Maybe we have to set the begin. Our software
put it to 100K. Okay, we just found a new use case for this.
Yes.
Yes. Ah, congratulations, Florian. Okay, so yes, Bode rules. Now, so as you can see, if we sweep backwards, maybe we have to increase the attenuator for one channel. If we sweep backwards, we can get rid of this discontinuity.
Yeah.
Okay.
Another question?
Yes, there's a question coming up. It's partly. It's no, some stuff is missing, but okay.
I think maybe it's just a dark description.
Ah, okay.
And I think.
Oh. Okay, it says we've had an instance when we finish a sweep, and at next sweep, the Bode 100 sweep starts sweeping with the last frequency.
Yes. This is the reason for that is that the Bode 100 source normally stays on with the last frequency it got as an information. If you want to prevent that the source drives out the last frequency you have measured, then you should set the source mode to auto here in the configuration. Then it will stop after a sweep. So then it will shut down the source and then it will start with the new frequency again.
We can demonstrate this if we go to single sweep. We just start the single sweep.
That was already the single sweep.
So, and after the single sweep, you will see that the source will change from green to gray. Yes, so it just changed. It's gray now. This means that the source is actually disabled. So when I start the next sweep, the next single sweep, it will start at the high frequency. So it will first change the frequency to the 1 megahertz, and then it will switch the source on. So this is also a nice trick to avoid that after a sweep has finished, the final frequency is outputted to the device on the test all the time.
Okay, I think we have to prepare the next webinar. Bernard, what do you think, or is there another question coming up?
No, I think there's just some discussion that we can focus on later on. So thanks everybody for participating. We will now prepare our impedance webinar, and it will we will then open a new webinar in a few minutes from now, and this time we will be on time because we're already back in our lab.
Thank you very much.
Thanks a lot for being with us. Bye-bye.